right, so I didn't really get any questions asked beforehand, so really the only questions I have are those that you'll ask in the uh, chat feature. Only thing I really like to say is next week is the start of the second exam, so I'm guessing we're going to have a lot more questions come next week. Your homework is due Friday at midnight at the end of next week, and then the following Sunday after that Friday at midnight is when your exam is finally due. So if I don't see any questions, picking the guitar today. What's up, Elijah? I think you're the only one watching right now, so whatever questions you have, feel free to ask them. Otherwise, I'm going to practice some chord exercises. All right, so the second part of the discussion board for Organic 1 is asking about the relative positions of axial versus equatorial for the different structures that are drawn. So let me bring it up. And we'll do number 4, not because I'm going to do number 4 just because it's the easiest one to build the structure for. So the first thing I'm going to ask you is, what's the name of this compound? And you should be able to see from this two-dimensional drawing that this is cis 1,2 dimethyl cyclohexane. So that's the easy part. Now, it asks you at the end, indicate if the two groups are both equatorial axial or if one group is axial and the other is equatorial. Now, let me get out my modeling kit. We can't say if an atom per se is axial or equatorial because we get interconversion of the axial equatorial atoms. So let me build my happy little model. And let's see if I have enough atoms to do this. 1, 3. I might have enough atoms to make this clear. Promise I'm about to answer your question. So let's say I build the full chair conformation of cyclohexane. And what I'm going to do is I'm going to attach, it's a happy little model. There are no mistakes. Well, there are, but you know, I'm not quite Bob Ross's level of optimism. So when we build them, we end up with axial and equatorial positions. So here I have the white atoms being the axial atoms, and they're axial because if I put them on my hands, they go up and down. And these white hoses here are going to represent, these flexible ones are going to represent our equatorial atoms. So when we are in the chair conformation, if we take the chair and we actually kind of tilt it so it sits sort of flat-ish, we end up with axial and equatorial positions. Now, the reason why we can't say if an atom is axial or equatorial is that if I take this, and I bend it, now I can flip them. So all my little hoses are now axial and all my round atoms are equatorial. But the only thing we can say is if things are axial or equatorial relative to one another, whether or not they both occupy axial and equatorial, or whether or not one is axial and the other is equatorial. So with these hoses, it's not like I can just flip one. All the white atoms are either equatorial or they're all axial, but I can't switch the tubes. The tubes are always in the opposite position. So there's a couple ways you can approach these types of problems. One is to build the model, which is the one I would recommend. The second is to memorize the pattern. But again, I would recommend building the model. So if we look at this cis dimethyl, so I'll pull off the atoms. So to build our 2D model, we're going to take our chair conformation and we're going to cram it down into a flat ring. And in this case, they're both cis. So this is what the molecule looks like as drawn. So when we draw it, we pretend that the cyclohexane ring is sitting flat. Now, in order to bring it to the chair conformation, we need to pick one, and I'm just going to arbitrarily pick one of them, lift to the carbon and put the one opposite directly across from it down, and this gives me my chair conformation. So if we look at it, we've got one methyl group axial and the other equatorial. Now, if we flip it, again, we've got one axial and equatorial. So for the cis 1,2-dimethyl cyclohexane, one is axial, one is equatorial. Now, there isn't a preference for one over the other because they are both the same size. If we go to the first one, the ethyl methyl. It's the same story. We can have one axial, one equatorial, but we can't get them both into axial or both into equatorial. Now, in terms of stability, it's more favorable for the ethyl group to be equatorial because bulky groups before the equatorial plane, because as you can kind of see, it gets further away from the structure. The axial is kind of stuck in this column that contains the cyclohexane ring. Now, if we go to the next one, we go, I'm sorry, the first one is trans. So if we do the trans, so for the trans structure, again, we crush this ring down so it's flat, and we've got one group above, one group below the ring, and if I just arbitrarily pick one up, I see now that they're both axial, or I can flip it, almost there, and now they're both equatorial. So for the first one, the trans 1-ethyl 2-methyl, we end up getting that they're both axial or they're both equatorial. So they're coaxial, coequatorial. But there's not really a way to say which one they are as drawn because this presupposes a flat ring where in reality we know that it's probably in the chair conformation. Now, it's going to spend most of its time with both of them equatorial because of energy reasons. When they're both equatorial like this, they actually end up moving away. For them to both go axial, even though they're away from each other, they're still next to these other axial hydrogens. But again, what we would say for the first one is that they are both axial or both equatorial. But for the cis version, the methyl groups are one's axial, one's equatorial. But they both aren't axial and they both aren't equatorial. And that's how you answer those types of questions. It depends on the position. So trans will be true if the second atom is on the second or is on the second position. So trying to think. So yes, if it's on the second or fourth atom. So if you see the second group and it's 2 or 4 relative to the first one, and they're trans, then you see this alternating with, you're going to see that they're both axial or both equatorial. If they are cis and it's 3 or 5, so if the second group is third or fifth position, they're cis and they're both axial, both equatorial. And then the reverse is true. If they're cis and it's on the second position, they're one's axial, one's equatorial. If yeah, you can work it out. I think I have a previous live stream where I tried to work it out. But there is a way to, there is a memorization as well. So let's say we have 2 groups on a molecule. We have the first, second, and third positions. So first thing we have to ask is the number on an even position? Yes. No. So this would be a, if we had something like a 1-2 molecule. So you've got one example where it's, look it up. We have one where the second one where it's 1 ethyl to, it's 1 ethyl, it's 2 atoms away, so it's actually the 1-3. But anyway, next thing we've asked is if they're cis trans. So if they're both cis and they're 2 atoms apart, there is a constant rule to it. I just don't encourage memorizing it because you can see what I'm doing right now. Like, you can try to memorize it, but if you don't use it all the time, you're going to forget. So if they're both cis and we pop one up, did it wrong. They're either both equatorial So the converse is that they're trans and one's axial and the other's equatorial. Now for the 1-3, it's just flipped. So the trans, they're both axial equatorial, and for the cis, there's one axial and there's one equatorial. So if we go to the 1-3 and we flip this into the Jericho formation, we have one axial, one equatorial. Also, if we take the same structure, we put it in the third position, we have one axial, one equatorial. Now, there is a bit of a nuance with this because when they're both axial or both equatorial, if it's 1, 2, then they're the opposite sides of the rings. If it's the 1, 3, then they're same side for the axial. But it's kind of a little nuance. When I used to tutor this concept really confused me because this is one of the things that Carrie does not explain very well, is how you can predict how they're axial or equatorial. And as far as going the other way, like it's just a mirror image. So 1, 2, 3. Yeah, you're welcome. No, the real hateful one. So if you look at 1, 2, and 4, those are also chiral molecules. So not only can you do the cis-trans EZ notation for them, you can also do RS as well. So the EZ, if we look above and below the plane of the ring, so for cis-trans, we can do it if we have two groups that are the same. So with these example problems given online, as long as there's like both of the carbons contain a hydrogen, you can use the cis-trans, and the cis-trans refers to the hydrogens themselves. But let's say we have 4 different groups. Attached between 2 carbons. So hydrogen, chlorine, fluorine, bromine. And we want to know if it's E or Z. So E or Z here is going to use the Kohn-Ingold priority rule. So the ones that you were using for the RS notation for test 1, those still show up. But instead of having to look at all 4, what we're going to do is we're going to take this and we're going to rotate it on its side. So we've got a bromine going up, fluorine going down, chlorine going down, and hydrogen going up. And we're going to look on the left side and the right side. So the left side, our highest priority group is down. And on the right side, our highest priority group is up. So the E here is INTGAN. Which means opposite. So in this case, this would be E. Oh dear. 1 bromo, 2 chloro, 2 fluoro, cyclohexane. Now the opposite of this is Z. So Z is zusammen, which means together. So if this was flipped, both of the highest priority groups are down and they're together. So we would say that this is Z, 1 bromo, 2 chloro, 1 fluoro, 1 fluoro, cyclohexane. But the E and Z here only refers to the proximity of the highest priority groups relative to the plane. So if they're on the same side of the plane, instead of saying cis, we'd say they're Z. If they're on opposite sides of the plane, instead of saying they're trans, we're going to say they're E, they're INTGAN. But this is used because if you say cis or trans, you're referring to 2 groups relative to each other. So if we had 2 hydrogens here, when we say this is a trans complex, we mean that the hydrogens are trans to one another, opposite one another. But if you say cis-trans with regard to a compound like this, it's not clear what's opposite one another. So if we use the CIP and we use the EZ rules, that becomes a bit more specific. Now, you can always use EZ for in place of cis-trans, but not vice versa. You can't always use cis-trans in place of EZ. Good. You're welcome. And this is when I start out with the RS, is that if you know the CIP rules for RS, EZ uses the exact same rules. So by this point, you're a little comfortable for figuring out where the priority rules are and working it out from there. Page 6 and 8 of the study guide. So let's see if I have a copy of it on the desktop. Ha, that monstrosity. On the upside, I didn't give any stereochemistry. I'm sorry, looking at the key. Correctly draw the following branched alkanes. Okay. I was like, man, that's a mean problem to give you for naming. So if your figures don't agree with the drawings, make sure this isn't just an issue of stereochemistry. So we have decane, 1, 2, 3. So decane has 10, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you've got 3 branches. We've got the 5-ethyl, so 1, 2, 3, 4, 5-ethyl. We've got 7-methyl, 6, 7-methyl. And one at the 4th position. Actually, that figure might not be correct. Because it looks like it should be 1 over, actually. 3, 4, 5 ethyl, 7 methyl. Oh, it should be 6, not 4. So that is a mistake on the key. So instead of saying 4,1,2,2-trimethylpropyl, it should say 6,1,2,2-trimethylpropyl. But as far as the compound itself, let's do the correct one, which is the 6. We have a propyl chain, so that's 3 carbons. 1, 2, 3. And it's 1, 2, 2 trimethylpropyldecane. So that's how it gets this structure. It's flipped over in my drawing, and also that should be a 6 trimethylpropyl, not a 4 trimethylpropyl. Other one, page 8. Correctly name the following alkanes. So on mine, oh, page 10. Okay. I'll say, like, really, you're struggling with that one. Ooh, okay, so nonane. So this is 4-ethyl, 6-methyl, 5, 2, parentheses, 2-methylcyclopentyl nonane. So nonane here is 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. We've got a 4-ethyl. 1, 2, 3, 4-ethyl. 6-methyl. And at the 5th position, we have 2-methylcyclopentyl. So the cyclopentyl, now anywhere it attaches to the parent chain, that's going to be the number 1 carbon. So our 2-methyl can be here on the right or there on the left. It doesn't really matter. We have bond rotation to kind of account for that. But that's how you get the answer that's in the answer key. It's actually a good question. Yeah, like the nice thing about, so this is one of the situations where the naming, going from the name of the formula is super trivial. Going from the formula to the name is super hard. So it's kind of like it was in Chemistry 1. So in Chemistry 1, when I teach it, we always start with going from the formula to the name because that's hard. Like you have the formula, particularly with transition metals bound to nonmetals, you have to figure out the oxidation states. There's a lot of work. But in the process of doing that, you begin to understand how all the components fit into the name. Now you're kind of seeing that with this too. We start with drawing the name from, getting the name from the drawing. You see, okay, I have to identify the parent chain, I have to identify the branches, I have to do the numbering. So the reverse is actually a lot easier because you're not restricted by the drawing. You can draw the nonane however you want to do it. And then you've got the numbers, so you just highlight the numbers in the position and start adding what's there. So handed to IUPAC, and honestly, I don't view the naming in IUPAC it's a lot easier than naming, definitely naming transition metal complexes in inorganic chemistry. But even in Gen Chem, I think it's a little bit more straightforward. There's like no calculations that are really involved. Second and third question on page 2. Correctly name the following chains. Three peaks. Goes down to 2 peaks. And up, and down. So the challenge with all these is tweezing out the longest carbon. So it's kind of a game of guess and test. So if I do 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 is going to be the longest. So this will be no name. I look at my branches. I've got methyl branches and an ethyl branch. And I've got 1, 2, 3, 4. So it's something ethyl, something tetramethyl. As far as numbering where the ethyl goes, I have 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. So no matter which way I ordered, I ended up getting the ethyl at the 5th position. So now we need to look at what happens if I start on the left side versus the right side. So if I start over here, I have 1, 2, 3, 4 is the first methyl position. If I start over here, I have 2 as the first methyl position. So I want to arrange the first carbon in such a way that the lowest numbers come first. So I have 2, 3, 4, 6. Tetramethyl no name. All right, page 3. Second and third question. That's definitely 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then I drop down, third valley. So I've got 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the parent chain here is decane. Now what about the branch? Well, this is the number 1 carbon, and we have to decide if we want to go left or right. So if we go left, we get 1, 2, 3, and we end up getting 2 branches. If we go right, we get 1, 2, 3, and we only have 1 branch. If you ever encounter a situation where you end up having 2 ways, basically in this case you get 2 propyl groups, 1, 2, 3, 1, 2, 3, you want to go with the numbering that maximizes the number of branches. And the reason being is that if you maximize the number of branches, typically the branches are easier to name. So if we go right, this ends up being 1 isopropyl propyl. If we go left, so we use this, it ends up being ethyl methyl propyl. Now, that is a longer name, but the ethyl and methyl branches are a lot easier to draw than something like an isopropyl. So with that being the number 1 carbon, it ends up being 1 ethyl, 2 methyl propyl, and as far as the decane goes, it's 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, 6. So 5, 1 ethyl, 2 methyl propyl, decane. The one beneath it's going to kind of follow the same reasoning. These are both decane chains. And I had to pick decane because it pretty much guaranteed you were never going to find a longer chain. So again, decane's our parent chain. We have an ethyl. Methyl. And then hanging off of this, we've got a propyl, but it's a methyl propyl. I'm going to have to kind of put it in there. So now with the methyl propyl, it's 1 methyl propyl. All that's going to be down there, and it's on the 3 ethyl, 5 methyl, 6 parentheses 1 methyl propyl decane. So the approach for these types of problems, again, identify the longest chain, find the branches, and if you have a complicated branch, just kind of put it in parentheses as a placeholder, name all the other simple branches. identify the position of this complicated branch, and when it comes to naming like the complicated branch, it's going to follow the same reasoning as naming the longer branch. It's just that now you've set the first carbon. You want to maximize branching, and instead of saying like 1-methyl propane, you're going to get rid of that A-N-E ending to say YL to indicate that this is an alkyl group. Again, the A-N-he here indicates that this is the parent chain and this is what's dictating the chemistry. Yeah, you're very welcome. And we'll talk about when we get to alcohols, that A-N-E ending is going to switch to OL. We always name it by the most reactive functional group. So right now we only have alkanes, so we don't have a choice. When we get to alkyl halides, the A-N-E ending still exists because we don't really view the halides as particularly more reactive than the hydrogens that are on the chain. The alcohols, though, those do a lot of chemistry. So when it comes to naming alcohols, this is going to switch to an OL, and instead of having everything else kind of weighed equally, we're going to favor the numbering system to favor the alcohol. Any other questions? Technically, there's only one correct way to name an alkane, but the nice thing about the IUPAC system is that even if you name it absolutely wrong, like you have the wrong numbering system, you don't follow the rules of more branching, you can still draw the right structure. And that's kind of a redundancy built into the naming system for hydrocarbons and organic compounds, particularly for simple ones, is that if you can name it completely wrong, meaning you don't follow the rules like you're supposed to, you can still figure out what the structure is. We will talk about, if you go into Organic 2, we do hit a point where the naming just becomes completely unwieldy, and we start dropping into trade names and we stop using rules altogether. But particularly for Organic 1, even if you name it wrong, you could still come back later. I could still figure out what you were drawing, even though you named it wrong. But I think that was part of the design when they did the naming for organic chemistry, was to make sure that even if you did it completely wrong, you could still get it right. This isn't true of something like non-metals with metals. If you get the wrong oxidation state, like you're getting the wrong compound. This is pretty much guaranteed that even if you name it wrong, you're still going to get it right. Gotta hand it to the Germans. Like, this was a really good idea. But again, when we start hitting Organic 2, and for me it was when we hit benzene compounds. And I will hand it to my Organic 2 teacher. She was very honest, like, we're not going to worry so much about naming anymore because you get so many rules that just completely contradict each other. And there are so many trade names that pop up, and people weren't willing to change, so there's like weird non-IUPAC names that show up in IUPAC naming. But this is benzene rings. Yeah, you're welcome. Again, feel free to ever ask questions or email them out in advance if you have them. Otherwise, this is just me practicing my instruments. You too. I'll see you next week. Yeah, I would still be here if there was no viewers. In fact, there's several live streams where it's just kind of me just kind of staring blankly at a screen. This technically counts as my office hours, and yeah, I'm supposed to be here available for students. If we miss our office hours, we're supposed to take vacation time for it. But it's also one of those like it's kind of your time to use. So I did kind of learn my lesson this summer about having office hours with nothing to do. A lot of it was just me kind of messing around. You could hear me tapping in the background. So that's why this showed up this semester was that I figure if I'm going to show up to a live stream and no one's here, I might as well be productive and practice an instrument. But there's only so much I can really do. This is actually a school laptop I'm working on. They gave it to me so I could do some video processing. It really doesn't have a lot of processing power. It can barely keep up with the streams. And I'm definitely not like going to do a lot of in-depth like work on like building packets, working on tests, things like that while I'm in the middle of a live stream because if I get distracted, I shouldn't say distracted. If I'm answering a student's question, I might forget where I was. So yeah, I'm still here. Even I've definitely had live streams where no one showed up to them and I just sat here for an hour. But yeah, definitely going to be here. Nope, this is budgeted directly into my schedule, and if you just want to sit here and lurk, that's perfectly okay. Um, Again, this is your time, so if you have questions, ask them. If you don't, sit back. I'm sure. Generally, at the start, I had questions to answer, but if anything, you get to listen to me mess around on a guitar or a banjo. Not comfortable yet doing the fiddle though. Yeah, that's also why I've tried to like get into the habit of like putting down my instruments. So if you're like trying to like skim through the video to see what I actually answer a question, it's when I put the instrument down. Um, yeah, I've definitely worried about that with some of these live streams, but I don't see how that's any worse than you having to sit through an hour of me just staring at a computer screen too. And by the way, don't feel bad if it takes 6 times for you to like, or even dozens of times for it to stick for you. Right now, I'm trying to like get back into antenna design for ham radio because I have a license and there's a long, interesting story behind how I got that license. But I kind of want to like mess around with it, but it's been so long since I've talked about how to work with radios, and it's really hard getting a lot of this to come back. I'm glad you learned a lot today. But yeah, felines, and I'm sorry, antennas kind of work by magic. Like they're like pH meters. There's a fair degree of witchcraft that actually makes those things happen. And some of it I am just not getting. And I've had to read like articles and books and so many things to figure it out. Everyone's got an Achilles heel. The chemistry course I hit that I genuinely never truly understood was quantum mechanics. Like, I understand quantum mechanics, but the chemistry version of it makes no sense to me with that stupid Bra-Ket notation. And I know part of it was I had a horrible instructor and several horrible instructors in a row that I learned nothing from. But it's a combination of two things. It's terrible instructors and a field of mathematics. Three things: field of mathematics that uses this absurd notation that I'm sure makes sense to the people who understand it. What am I always drinking? So every week I make up a gallon of kombucha, and this is the leftover sweet tea from making the kombucha. So the brown liquid, just basically sweet tea. I make my kombucha pretty. I don't make it with a lot of sweet tea, so I like it versus traditional sweet tea, which is super sweet. So this is about a half a cup of sugar and almost a gallon of water. And it's just a nice break from water. I drink water throughout the day, but honestly, I get tired of it. The book I'm practicing for my guitar has a severe love of the D minor chord, and I have never really had to play it before. It is driving me bonkers. was trying to get good at guitar in grad school, I used to use a strategy called Around the World. And so with Around the World, you pick one chord that you always have to go back to. And your goal is to go to all the other chords, but you always return to the starting chord. So if you do D, or you do D, G, D, A minor, D, A, D. And the idea is that it kind of gets you used to anticipating how your finger should be going to the next chord. Never once did I ever do D minor, and I've done some weird chords. Yeah, the whole stupid hold six strings down with one finger and like somehow get the other three to be in the right position. Never learned bar chords. I should. I've heard they're quite powerful. And I really need to get better about doing F as a bar chord because I keep trying to do the hold two fingers down. And F is my Achilles heel. I cannot chord F to save my life. Like right now it's fine, but to go, oh, D, F. Especially when people go like C, F, F, C. It's like, how do you do that? Like C, F, C. Yeah, like I don't understand the love of the chord of F. Like just people are just born with their hands naturally in that position. This is just not a natural chord. It sounds pretty, I like it, but it's like, oh, go from a D all the way to F. Actually, what's even funnier is when you get a song and no one has changed the key. Like they wrote, they don't realize what a capo is, and so you get like these absurdly like C sharp, G sevens, and you read through it and you're like, what on earth? Like you're trying to figure out like what weird bar chord this is, and you realize they don't understand what a capo is. Like if you put a capo on, it's like C, D, really actual real chords. All right, so we're at the end of the hour. Thank you all for showing up. Yeah, and feel free to email any questions, and I will talk to you all Monday. Have a good weekend.